Hi everyone, my name is Yves Fauser. I'm a technical product manager in VMware's Networking and Security Business Unit. And I'm going to talk about Kubernetes networking with NSX. Standard disclaimer slide, I guess you saw that one before. So what's Kubernetes? Kubernetes is a container orchestration system. So you come with your own container images that you packaged in some way or form. And then you give it to Kubernetes, and Kubernetes makes sure that it runs those container images or these containers in a distributed fashion on the nodes that we will talk about in a second. It ensures that you are in your desired state. So you tell it, hey, run me 10 images of that container, and it will do that for you. I don't have, in this quick talk, I don't have all the time to go into all the architectural details, and there are a lot of sessions that you can watch that introduce you to Kubernetes itself. Now, for the NSX integration, it's important to understand two pieces. One is the node, which is the gray box you have up there. That's where you run your containers in. And then the blue box is the Kubernetes master, or the masters, if you build them up in a highly available fashion. And we integrate on both sides, on the node and on the master side. On the nodes, those pods, and I will talk about pods in a second, that get created and that hold those containers, they need to be attached to the network. And that's what we take care of with NSX. So we attach those pods to NSX networks, to NSX logical switches, and we give those pods a networking home, so to say. And then on the Kubernetes master side, we watch for creation of objects. So if a new pod is created, if a new construct like a namespace is created, we take action and we create the needed elements in NSX in our networking solution. And I'll go into a demo later on that will show you exactly that objects are created in Kubernetes and we have a resulting effect on NSX. So I already mentioned the name pod, and that's a confusing term. In Kubernetes, we are talking about pods, which are groups of containers running on the same node, so on the same resource that runs those containers. Why do we have this construct in Kubernetes? It's to be able to provide a single functional unit that runs multiple processes. You can either have a container running a single process or have a container run multiple processes. But if you run a container with multiple processes, you need some init system in there that starts these separate processes. And that's not the nicest way of doing things, because then your containers more and more resemble like full-fledged VMs that run multiple processes. So, but there are things where you need multiple processes. One example here is my web server and my logging process. I have a web server serving the request, writing logs out, and I want some syslog daemon to send them somewhere else, right? To be able to do that, I need to run two processes. And the way Kubernetes does that is by saying, okay, we have two containers, one container for the web server, one container for the logging, and they are both able to access the same file system resources, and they are having the same connectivity to the network. So now my web server serves the request, writes the logs to disk, and then the syslog container gets that logs from disk, and then is able to send out those logs to some aggregator service, etc., etc. So for us, it's important that you understand that a pod is what we attach the network to. And a pod has an IP address, and that IP address needs to be routable inside of the Kubernetes cluster. And that's what we take care of in NSX, to route the traffic in and out of those pods. Then we have an important construct, which is the namespace. In Kubernetes, the namespace started off as a name uniqueness construct. So here in this example, I have two pods called Redis master. And if they would be in the same namespace, their name would collide. Kubernetes doesn't have concepts like UUIDs for resources, so they need this Redis master needs to be in two different namespaces, in two different passes to have a unique name. But then the namespace evolved to be a tenancy construct. So we now have role-based access control per namespace. So you can say which users or user groups are able to access what resources on the namespace. We have quota per namespace, so things like CPU limits, memory, etc. are bound to the namespace. And now we also introduced Kubernetes network policy, which is bound to the namespace, where you can say what is allowed into this namespace and what is allowed to communicate inside of the namespace. And we are fully supporting that with NSX2. So you can microsegment all the traffic inside of your namespace. You can say what part is allowed to talk to what other part on what TCP or UDP ports, and what is allowed into the namespace. Okay, so what did we build? The first thing we decided is we want to give this tenancy construct of the namespace a network meaning. And we create a network topology per namespace. So we use our NSXT version for that. And in NSXT, we create what is called a tier 1 router. That's a tenant router. That's the blue one that you see here. And that tier 1 router is associated to the namespace and gets IP addresses, holds a subnet that we also assign out of the IP address management of NSX. And every time a new namespace is created, we create a new tenant router, a new tier 1 router. We attach logical switches to it, and those logical switches are overlay networks that span all the nodes. And then we attach the pods to those logical switches. That means the pods get an IP address where they are identifiable as belonging to that specific namespace. While in other solutions, you basically have IP addressing per node and not per namespace. That makes a big difference because now you can match on those network constructs, you can match on subnets, you can match on SNAT IPs in the outside world, and you know where your traffic came from and to what tenant it belonged. Then since we are attaching that pod with a logical port to our logical switch, we have the same capabilities as we have for VMs. So we place a firewall in front of the pod, so we can really microsegment each individual pod. We have all things like counters. We can redirect traffic to a monitoring station using mirroring. We export flow records that can be analyzed. So everything that you can do with a VM interface, you can now do with a Kubernetes pod. And then on the north-south side, our tier 0 router is a high-performance gateway to route to the outside world that uses Intel's TBDK to have a very high performance. One additional thing that we have is we have the ability to define when we create the namespace if it should be behind NAT or not. So with that, you can have direct routing if you want. You can announce that namespace network to the outside world using BGP. Or you can say, no, that network needs to be behind NAT, and I don't want to expose those IP addresses to the outside world. So we have both in the same solution, and you can go back and forth between both. OK, enough of the theory. Let's look at a little demo video here. So here's my environment. And you see I have 3 Kubernetes nodes running as VMs on a vSphere cluster. And in addition to that, I have one VM, which is my Redis database. So I have my database outside of the Kubernetes cluster running as a VM. And what we see here is the logical switch where my database VM is connected to. And this is the interface it has. And we see the VM name here. And that's important because we will match on that VM name later on in the policy. Now let's have a look at the Kubernetes side. Here are my namespaces in Kubernetes, and one of it is called Yelp app. And that one corresponds to a logical switch and a logical router in NSX. Okay, so when I created the Yelp app namespace, it created those constructs for me. Now what I'm doing here is I'm setting the context of the CLI tool to use that namespace. And I'm pointing now Kubernetes to the definition of this app, which is on GitHub. And here's the web front-end definition, and you see it includes a label called sec group with the value web tier. And down here, we have the sec group app tier. Those labels are copied into NSX, and so then we can match on those in the firewall rule set later on. And down there you also saw the URL that we will use to access our application. So now I'm pointing Kubernetes to my GitHub. It creates all those objects. I'm watching for what happens. Up here you see we are in the container creation phase. They will flip to running in a little second. Here we go. And then the last thing we'll look at is, well, first of all, here you see down there we have the labels again, the secgroup web tier, it got copied. And here's the URL we want to access. Before we access the URL, let's have a look at what was created on NSX. Those are the logical ports that got created for the parts. And they are child interfaces of the VM interface of the node VM. And now if we look into the port itself, you will see down there that we copied the labels to tags onto that port. So now we can match it in the firewall rule set using those tags. And if you use network policy with Kubernetes, it basically also creates all the dynamic matching criteria and firewall rules for you. Now here I configured it statically. So I have 3 groups that dynamically match objects. And the first one is matching my database port. And it's matching that on the VM name. So as soon as I have a VM named Redis, it's matching that group. For the app server group, I'm matching on the port tags that you saw before. So the labels that I got from Kubernetes are matching that group. And now in the firewall rule set, I use those groups to say, okay, web servers to web servers should not talk to each other. We'll drop that traffic, right? Then web tier to app tier, we allow that traffic on that specific port. And then, okay, continuing app tier to DB tier, which is my database VM. I'm allowing traffic on 6379. And then I'm allowing DNS and I'm dropping everything else, okay? So now we can finally see if the application works. And it's a voting app, so I can vote for my favorites here, and I press the button, and then down it's added to the Redis database, okay? So what happens if I drop? Obviously then the traffic will be dropped. So my nice little application is broken. Let's refresh. And you see now I can't access my data anymore from the app tier, so I can't vote anymore. I don't see the results. So how would I go about troubleshooting that? We have a nice tool which is called TraceFlow. And with that tool, I can inject synthetic traffic, fake traffic into the system. So I'll just select the source port to be the app pod, and the destination to be the virtual machine, the Redis database. And then in the advanced tab, I can now select, okay, I want to send TCP traffic, and I will use some ephemeral port, 10,000, I think I took here, yes. And then the destination port is 6379. And then I send that synthetic traffic, and NSX will now map the path of all those logical objects. And you see on the left everything that was traversed, but the first one is already dropping, which is my firewall rule, okay? So I know it's now rule 1085, which is the problem. Can go into my rule set, and indeed it's 1085. Could change that to allow, and then it's allowed again. Okay? And then guess what? If you go to the Yelp app, you will see that it works again. Okay, and that's pretty much what I wanted to show you. So we're unifying VM to pod traffic. We're giving microsegmentation to Kubernetes Parts. We enhance visibility of the container networks. And it's a fully supported solution for Kubernetes with NSX. And thank you for your time.